Jai Hind students. In today's lecture, we will cover 8085 architecture, which is one of the complex topics of microprocessor. Plus, it is one of the topics which is most frequently asked in university exams, in internal as well as external exams. So, let's begin with the topic 8085 architecture. So, in today's lecture, we are going to cover 8085 architecture and the functional units of 8085 microprocessor. Moving on to the topic, you can see that the entire architecture is actually divided into 5 main functional components. These functional units include, first of all, we have including W, Z, B, C, D, E, H, L registers, stack pointer and program counter. Here we have instruction register, instruction decoder. Then we have accumulator, temporary register and flag. So all these registers make up the part of your register unit. Next we have arithmetic and logical unit. So here we have ALU, arithmetic and logical unit. Next is timing and control circuitry, which is considered as the brain of this 8085 architecture. Then we have serial input output control unit, the 4th unit, and the 5th unit is interrupt control. As you can see, there are 8-bit internal data buses and address buses of 16 bits which are running throughout this architecture. So, we will begin with the first unit, that is register array. So, the register array, first of all, the most important register here is accumulator. As the name suggests, it is accumulator. In order to accumulate, we need to collect something. So, the name signifies that we are collecting something. So, accumulator is a special register which is an 8-bit register which is used to hold the result of every arithmetic and logical operation. So, it is an 8-bit register which is not only used to perform the arithmetic and logical operations, but also it is used to store the result of every ALU operation. Next is arithmetic and logical unit. The arithmetic and logical unit is responsible for performing all the arithmetic and logical operations. The arithmetic operations include addition, subtraction, multiplication, division, and the logical operations include AND, OR, NAND, NOR, XOR, rotate left, rotate right, and that type of instructions. Then moving on to the general purpose registers, 8085 microprocessor has 6 8-bit general purpose registers. These are registers B, C, D, E, H and L. Now, the most interesting thing here is you can use these registers individually as 8-bit registers, or if you want 16-bit register pair, then you can club these registers. But the pairing always happens like this. B is paired with C, D is paired with E and H is paired with L. Whenever we are using a register pair like BC, DE, HL, that becomes a 16-bit register pair. Otherwise, if we are using it individually, it is a separate individual 8-bit register. Program counter. Now, program counter is one of the very important registers of 8085. It can be asked along with the entire topic architecture of 8085. Although it is sometimes also asked individually in 2 marks questions that what is a program counter, what is the role of program counter. So first of all, it is here it is important to understand that program counter is a 16-bit register. Okay, so it is a 16-bit register which holds the address of next instruction to be executed. Okay, we all know that the programs of microprocessor 8085 are stored in memory. So, there are specific locations in memory where the program is stored. Alright, so the program is stored in memory and we can just access the memory like this is a microprocessor MUP and this is memory. So, at specific locations of memory, I am having my program stored byte by byte, instruction by instruction. So, MUP needs to fetch the instruction from specific locations of memory. If this is memory and this is location number 2000, the MUP has to fetch the instruction which is stored at this particular memory location. In this case, the program counter register of microprocessor 8085 will hold the value 2000. It means that program counter is a 16-bit register which is used to hold the address of next instruction to be executed. Next is a stack pointer. So stack pointer again is a 16-bit register. What is the role of stack pointer? We all know when data is compiled in the form of stack, when data is in a stack entry. So we have stack positions like this. And suppose this stack is full up to here, 1, 2, 3 and 4. This is the last stack entry. So the stack pointer will be holding the address of this last stack entry. Okay, stack pointer का role आएगा when you are operating, when you are dealing with stacked datas. Next, we have temporary register. तो आर्किटेक्चर में आपने accumulator के just side में एक register देखा था. It is temporary register which is an 8-bit register again. So it is a register which is used to hold the data temporarily during the execution of any arithmetic and logical operation. At the end of this video, I will explain the entire working of 8085 architecture with the help of a small instruction. Then the role of this register will be more clear to you. So temporary register is 8-bit register which is holding a value temporarily during the execution of any instruction. Next, we have instruction register and decoder. Whenever an instruction is fetched from the memory to the microprocessor, that instruction is saved in the instruction register and decoded in the instruction decoder. Another very important register, flag register, which comes along with 8085 architecture. Also, individual question भी इस particular topic पे बनता है that what is flag register. So, flag register is an 8-bit register which actually indicates the status of the result that we have obtained in the accumulator. Okay, the result that we have obtained in the accumulator, it is stored in the accumulator, but the conditions of that result, they are depicted by your flag register. So, this flag register is actually having 5 1-bit flip-flops. And the positions are like this. We are having an 8-bit register starting from D0, D1, D2 up to D7. And on these bits, we are having, at D7 bit, we are having S. Here S indicates sign flag. At bit position D6, we are having Z. It indicates 0 flag. At bit position D5, we are having don't care. Here X means don't care. So here we are not having any flip-flop. At position D4, we are having AC, which stands for auxiliary carry flag. At position D3, again, there is don't care sign. Then at position D2, we have parity flag. And finally, at position D0, we are having carry flag. So in this way, there are 5 flags which are in a function, they are functionalized by 5 flip-flops, 1-bit flip-flops. Now these flip-flops can be set or reset depending upon the condition of my result. Okay, when the flag is set, it holds a value 1. Whenever a flag is set to be reset, it holds a value 0. So moving on to the various registers, first of all, we have sign flag. So whenever we talk about the signed numbers, signed binary operations, in those operations, the value of this MSB indicates whether my number is positive or negative. And the sign flag is set if we have a negative number, that is when we have 1 at the MSB position. Otherwise, this flag is reset, that is 0 value is passed in this flag if my number is positive, or if at the MSB I am having 0 value. How will you decide? Let us see, for an example, you are having 2 binary digits. Okay, 2 binary numbers are there. The addition of these 2 binary numbers gives me this result. This is my result of binary addition, and this is carry. The carry will not be counted as a part of result. This is carry. So in your result, this is your least significant bit, LSB, and this is your most significant bit, MSB. Now, if in your result the MSB is 0. It indicates that your number is positive, and in that case your sign flag is reset, means it is holding value 0. If your MSB in your result is 1, digit 1, in that case the sign flag is set, because in that case the number is set to be negative. So the value that sign flag holds, it depends upon the value of MSB in your result. If MSB in your result is 0, sign flag will be 0. If MSB in your result is 1, the sign flag will be 1. Next, we move on to the 0 flag. So what is 0 flag? 0 flag is set or reset depending upon whether my result is 0 or non-zero. Here you can see that the result is all 0. In such a situation, when my result is all 0, the 0 flag is set, meaning that the 0 flag will carry a value 1, or the 0 flag is set when my result is all 0. Okay? On contrary to this, the 0 flag is reset, or we pass the value 0 to it when my result is non-zero. Next we have carry flag. So carry flag is set or reset depending upon whether carry is generated from D7 bit or MSB bit or not. Like this, we can see this example and understand the operation of carry flag from here. So here 2 binary bits are being added and a carry is generated from MSB. This is the MSB or D7 bit. This is D0, D1, D2, D3, D4, D5, D6 and D7. The last bit is D7. So whenever a carry is generated out of D7 bit or whenever a carry is generated from the MSB position, we know that the carry flag will be set. That means carry flag will contain value 1. And it is not about the addition only. In subtraction operations also, if we have a borrow sign there, if we have borrow digit there, then also carry flag will contain value 1, or we can say that the carry flag will be set. Next we have auxiliary carry flag. So what is the condition for auxiliary carry? Now you know that these bits are ranged from D0, D1 up to D7. Whenever there is a carry generated from bit D3 to D4, in those situations auxiliary carry flag is set. Here we have D3, अगर हम इसको पूरा ऐसे हाफ में डिवाइड कर दें, so here we have D0, D1, D2, D3, D4, D5, D6 and D7. So when carry is generated from this position to this position, that means when carry is generated from D3 to D4. In these situations, my auxiliary carry flag is set. That means it will contain value 1, otherwise it will be reset. Last one is parity flag. Now, the setting or resetting of parity flag depends upon whether my result is having odd parity or even parity. Here, odd parity and even parity means the number of ones in my result. If the number of ones in my result is even, then I say parity is even, and in this case, the parity flag is set. That is, it will contain value 1. Otherwise, if my result is having odd number of ones, then I will say that my parity is odd, and in that situation, the parity flag will contain 0 value. Next unit of architecture is timing and control circuit. Timing and control unit is behaving like a brain of this entire architecture. It is actually passing signals to the various sections of your architecture and telling people what is needed to be done in order to execute a particular instruction. Okay, so the timing and control circuitry consists of 4 different types of signals. First of all, we have control signals. So these are the signals which are used to control the entire architecture, including ready signal, read bar. Here this sign means complement, read bar, write bar. These two are active low signals, means these signals will be activated when we pass the value 0 to them. Okay, and address latch enable. So the control signals include ready, read bar, write bar, address latch enable. These are the signals which are passed when a microprocessor is executing some control function. Then we have status signals, which includes S0, S1, input output / memory bar. Again, here we have memory bar. So this signal is again active low signal. That means it will be activated, memory will be activated when we'll pass 0 value to it. Okay, so status signals are telling whether what machine cycle my microprocessor is performing, depending upon the value of these three status signals, S0, S1 and input output / memory bar. Then we have DMA signals. DMA signal stands for direct memory access signals. So whenever my memory is being accessed directly by the IO devices, by the input output devices, in those situations these two signals come into play. One is hold and the another one is HLDA. HLDA is actually the acknowledgement for hold signal. Okay. And in this situation, the input output devices directly accesses the memory and the microprocessor go on hold situation. That's why the signal's name is hold and its acknowledgement is HLDA. Then we have reset signals which are used to reset the microprocessor. It includes reset in and reset out. And this reset in signal is also active low signal, that is we are having a bar over it. So these are all the timing and control unit signals which are used to control the various parts of my architecture in various situations. Next we have interrupt control. So there is an interrupt control unit in the architecture which includes 5 different types of interrupts. Inter, RST 7.5, RST 6.5, RST 5.5 and trap. These 5 are the different types of interrupts in microprocessor 8085. Now here it is important to understand that what is an interrupt. So it's understand it in this way. Interrupt means, the word interrupt means disturbance. So whenever microprocessor 8085 is executing its main program and any interrupt signal comes, any interrupt request comes, then it has to hold its main program, access that interrupt request, and then after that interrupt request is completed, then only your microprocessor 8085 can switch to its main program. So the word interrupt, we can understand this word in English also. The word interrupt in English means disturbance. Here also it means disturbance. That is, once an interrupt signal comes, the microprocessor cannot execute its main program. It has to stop its main program. It has to access the interrupt request, and after it is completed, it can finally go back to its main program. Okay. So we have 5 main interrupt signals including trap, RST 7.5, 6.5, 5.5 and inter. Another important unit is serial input output control. So serial input output control includes 2 different signals, serial input data SID and serial output data SOD. Actually 8085 microprocessor, it takes the instructions serially bit by bit in binary terms 1, 0, 0, 1 and it outs the data. It outs the data serially bit by bit. So for this we have serial input output control, and for input of data we have SID, serial input data, and to out the data we have serial output data SOD pin. Next we have address buffer and data buffer. So the address bus in 8085 is 16-bit. We have 16-bit address bus and the data bus is of 8-bit. 8-bit data bus. In order to reduce the number of pins, the lower order address bus is multiplexed with data bus. So we have signals, lines from AD0 to AD7, which are the multiplexed form of address and data bus, and higher order address bus A8 to A15. Okay. Another important thing here is to understand that address bus is always unidirectional because a microprocessor has to access a particular memory location. Okay. So address bus is always from microprocessor to memory, from microprocessor to IO. Okay. But Data bus. Data bus is bidirectional. Why? Data bus is bidirectional because microprocessor can send the data to IO or memory, or it can receive the data from input output devices and memory. That's why data bus is always bidirectional and address bus is always unidirectional. Now, we can move back to the architecture and we now can connect all these pieces together and build the entire architecture. So, here we were having the registers which we talked initially. Then after the registers we have arithmetic and logical unit which is performing my mathematical and logical functions. Then I am having the timing and control circuit which is the brain of this entire architecture. Then I am having serial input output control for serial entry of data and serial exit of data. And then I am having interrupt control unit which is having 5 different interrupts. Okay. Now I am taking an example of a small instruction with the help of which I will explain the entire architecture to you. Let us assume that we want to execute the instruction add B. Okay. Now to do this and to execute this instruction, what will be the output? What will actually happen when we pass this instruction to 8085 microprocessor add B? It means that the contents of accumulator will be added to the contents of register B and the result will be saved in register A, accumulator. Okay. That's why I say accumulator is a special type of register which has a special power that it can hold the result of every arithmetic and logical operation. Okay. So if I am giving an instruction add B, it means that the contents of register A will be added to the contents of register B and my result will be saved back to register A. Okay. So the program will start from here, this PC. Okay. Start from here, this is your MUP and this is your memory. And let us assume at memory location 2000, we are having this instruction add B. Okay. This program is saved in memory. This program is saved in memory and your MUP has to fetch this instruction to the microprocessor. So for this, the program counter PC will come into picture first. This PC will hold the value 2000. Why? Because this is the starting address of my program. Okay. Now PC will hold this address 2000. This address 2000 will go from address bus to memory and this instruction will be fetched back to microprocessor. Okay. This instruction will be fetched back to microprocessor and it will come through this data bus. Through this data bus, this instruction will come here and to this instruction register add B. This instruction will be recorded in your instruction register. Okay. So with this, the first step of your microprocessor operation is completed. Your microprocessor always works in 3 steps: fetch, decode, execute. So fetching is complete. You have fetched the instruction in the instruction register. Now the second step is decoding of this instruction. So now this instruction will be decoded in the instruction decoder. Okay. Once the instruction is decoded, we will start with the execution of this instruction. For this, this instruction decoder will pass the signal to timing and control circuitry. Now, timing and control circuitry will realize what is needed to be done. What is needed to be done? We have to add the contents of A and B and store the result in A. So this timing and control circuitry will send an signal to accumulator. Simultaneously, it will send instruction to B. Okay. B will save its data. B will send its data to this data bus and B's data will be recorded here temporarily. Okay. As soon as the timing and control circuitry receives a message that A is added to B and store the result in A, it will send a command to B. It will instruct B to load its data on this data bus. Through this data bus, the data of B will be recorded here in this temporary register. Now the data of A will be added to the data of B, which is saved in this temporary register. They both will be added in ALU, A plus B, and ALU will again send the data through this data bus to accumulator and the result will be saved here. The result of A plus B will be saved here in the accumulator. So this is your entire architecture which we have studied today with its various functional units and what are its major roles. That's all for today. Thank you, students.